Hi, welcome back to this video series on cryptography. In the previous segment, we talked about pseudo-random generator and how we test whether a given generator is pseudo-random or not. We defined the notion of distinguisher, and we talked about a probabilistic framework that is used to distinguish pseudo-random generators from a truly uniform generator or a truly uniform number. Okay. In this segment, I wanted to cover a few more details that were left out. First of all, I wanted to answer the question related to the quality of the output of a generator. Okay, suppose you have a generator G, pseudo-random generator is G, and that takes a seed S. Okay, seed S is a secret. S is a secret seed. Let's assume G of S takes an n-bit seed, right? S is an element from this space of all n-bit strings, or set of all n-bit strings, right? And returns an element, say, in the set of all strings made of binary strings, of course, of length 2n. Okay, so you send in n-digit number to G. It gives you a 2n digit. Say, for example, if n is 10, you get output as 20 digit. That's nice, right? You are sending a small number, you get a large number. Okay, that's really nice. But what about the quality of G of S? Is it uniform? Okay, is it uniform in the space of all possible 2n strings? The answer is no. Even if it is a very good generator, from a probabilistic point of view, we discussed the definition of distinguishability. Still, a generator like this that takes an n-bit string as an input and gives you back a 2n digit as an output need not be uniform. Okay, so why do I say that? So let's reason about it. So let's assume for a moment the generator is like a 1-1 function, right? How many possible values are there for S? Okay, well, S can be starting from 0 all the way to 2 power n minus 1. That means there are only 2 power n possible values for S, right? So imagine like this, your seed set. What are the possible values for your seed set? It can be 0, 1, all the way up to 2 power n minus 1, which means there are 2 power n possible values in your seed. Okay, and we map G is basically transforming your seed into another set, right? What are the possible values of this set? It can be 0, 1, 2, all the way until 2 power 2n minus 1. Okay, these are the possible values of the output of G. Okay, now comes the question, why do I say that the output of G of S need not be uniform? Okay, the reason is simple. How many elements are there in the output of G of S? Let's assume G is 1-to-1 for a moment, which means the output of G is a subset of all possible 2 power n values, right? So some elements, maybe it is picking this. So how many elements will be there in the set of all outputs produced by the generator G? Doesn't matter whatever S you plug in. Of course, S has to be an n-bit number. How many elements will be there? It can be at most, I will put it less than or equal to as an at most symbol, right? At most what? At most 2 power n, because we call G for all possible value of S starting from 0 to 2 power n minus 1. Therefore, G of S will be mapping to 2 power n possible values. Okay. But what about the size of this particular set? The range of G. The size of this particular set is, let me call it range. Well, range of G is basically 2 power n number of elements, but I must have said wrong. The range of G is 2 power n elements. How many elements are there in the set of all possible strings you can form with 2n string length. It's clearly 2 power 2n, right? So what we are dealing with is now 2 power n by 2 power 2n. Okay, so if you pick an element randomly from this set of 2 power n elements, what is the probability that, let's say I'm picking an element here, okay, some element I'm picking, say let's call it w, okay, what is the probability that that w was produced by g, meaning some g of s maps to w? Okay, I pick a w here randomly from the set of all 2n strings, right? How many possible 2 power 2n strings? There are 2 power 2n strings available, right? And I'm asking a question, what is the probability that that w was produced by a g? Okay, remember g produces only at most 2 power n elements. Okay, so the probability that a randomly chosen w is an image of some element from the set S, right? This is one particular, this is one particular seed. Okay, the seed is over here, let's say small s, and this is capital S. Okay, anyway, so generator takes a seed as an input. Okay, so what is the probability that particular w is an element of the set of all images produced by the generator? Is just 2 power n by 2 power 2n. Okay, so let me summarize this clearly. We have two sets here, right? One is the domain set. This is called the domain set, 0, 1 power n, meaning set of all n-bit binary strings. And then you have a range set. Okay, what is a range set? Set of all binary strings of length 2n. Okay, what is the size of the range set? The size of the range set is 2 power 2n, right? That's 2 power 2n possibilities are there in the uniformly chosen set. Okay, but uniformly chosen, if you choose an element from that set, there are 2 power 2n possible values you can choose. Okay, but G is not going to cover all the 2 power 2n elements. G is only going to cover 2n elements out of this 2 power 2n possibilities. That's the reason why I wrote the fraction. Okay, if you simplify this further, what you get is 2 power minus n, right? Which is basically very, very negligible. If n is large, it's very negligible. So what is the point I'm trying to get across is that the distribution of G is far from uniform, right? Only a small fraction of all possible 2n strings can be present in the range of the numbers generated by the generator G. Okay, so that's basically what I wanted to show to you on the first part. Okay, so what about the design of the distinguisher? Let's move on to the next part now. Suppose we would like to design a distinguisher, right? And remember, for the generator to be considered as a pseudo-random generator, any distinguisher you designed must satisfy this property. You feed in some, say something like this. For some seed, yes, you call G, it gives you some number, and you feed that number to D, and we're asking what is the probability D returns 1, right? This is basically what we do first step. What is the probability that D returns 1 when it is given an input G of S? S is the seed. And then we do the same with what is the probability that if you feed in a truly random number R, that returns 1. Okay, if these two probabilities are close to each other, right, that means we have not learned nothing about G. We don't know how G behaves, essentially. That's basically the intuition. We subtract these two probabilities, and then we say if the difference between these two probabilities is negligible, then we claim that we learned nothing about G. But there is a caveat here. What if we let D to run exponential time? Okay. In that case, there's a small problem. We can't do that. In the previous part of the discussion, I talked about the distribution of G of S. Okay. The distribution of G of S is far from uniform. So you could start a brute force attack like this. Let me show you the idea more concretely. So I wrote a Python program to demonstrate that particular idea. Okay. Let's directly get into the design of a distributed design of an exponential distinguisher. Okay, so what is the exponential distinguisher doing here? It's starting a for loop. It is going to try all possible seeds starting from 0 all the way to 2 power n exclusive, and then it calls the generator at each point until it get a hit. Hit means it find an S that maps to a given W. At that moment, it says it returns 1, otherwise it returns 0. This is a distinguisher that can break any pseudorandom generator, right? Because all it does is it is repeatedly calling the generator for all possible seeds until it matches the given W. Okay. Now we can reason about it. I'm going to show to you a generator. You don't need to know about HMAC at this point. Assume the generator is doing like this. It takes an n-bit number as an input and returns a 2n-bit number as an output. Okay, that's the only thing you need to know. It takes an n-bit number S and returns a 2n-bit number as an output. It's just little HMAC logic. Okay, so we believe that the generator G is a pseudorandom. That's the theoretical assumption we have. It's also true in practice. There is no known attack on HMAC in terms of breaking it. But what I'm going to show to you is that the distinguisher D can tell whether the W is coming from HMAC or not. Okay, because it's trying all possible seeds. Okay. So I'm going to, of course, do it for a small key size just to get the idea across. Okay, so we are doing all possible seeds now, right? How am I designing the experiment now? The first step is, don't worry about why am I choosing 10. I'm just trying to run it 10 times, the same experiment. I'm choosing an 8-bit key, which is really tiny, but I wanted to get across the idea of brute force, how we are able to distinguish between a pseudo-random function and a real pseudo-random generator and a uniform generator, right? So we select a seed randomly. We call the pseudo-random generator, which will give us a 2n-bit word W, and then we call the distinguisher. Okay, and we count how many times the distinguisher returns 1 for our input W, which is coming from the output of a pseudo-random generator. We do the same now with picking a uniformly generator number from the set of all possible 2n-bit strings. So we pick 1, and we also count whether the distinguisher is returning 1 in that case. If it is, we increment uniform counter, and at the end I'm printing how many times did I get 1 from the distinguisher when given the pseudo-random output as input, and when giving a truly uniform number as an input for the distinguisher. So let's run it. Let me show to you when I run it, what is the output. Okay, I'm going to now run this and show to you the behavior of my distinguisher. Okay, it's an exponential distinguisher, right? It's going to run for all possible seeds, but I made the seed size so small. Looks like I don't see the run button. Yeah, here it is. Okay, so what you're seeing here is interesting. We ran the distinguisher feeding a pseudo-random input, right? 10 times we ran. All the 10 times the program returned 1, meaning we hit the line number 24. Okay, by trying all possible seeds, the distinguisher was able to tell that our W is coming from coming from a pseudo-random generator. On the other hand, when I call the D with the W being a truly uniform value, 2n-bit value, it never got to line number 24. It never got to line number 24. That's interesting. N is the seed size, by the way. Okay. So when I feed my W with a number from Python's random number generator, I never got to line number 24. Okay, that's pretty interesting. So what it is telling us is that, okay, let's reason about it from a probability perspective. We ran 10 times. All the 10 times the distinguisher returned 1 when given as an input from a pseudo-random generator, and returns all the 10 times returned 0 when it was running with a truly uniform random number W. Okay, that tells us that the distinguisher was able to distinguish these two distributions. Okay, does it mean that the HMAC is broken? Okay, so that's a difficult question to answer. What I can answer though is that the distinguisher design is incorrect. Okay, meaning we shouldn't be allowing the distinguisher to run exponential time, right? If we run it to, if we allow the distinguisher to run exponential time, you can never design a pseudo-random function, right? A pseudo-random generator, for that matter, because the pseudo-random generator has an output which is already not uniform, right? It's far from uniform, to be more precise. So any distinguisher that is allowed to run exponential time will keep trying all possible seeds until it find a seed which matches the W, and then it says, yes, it must be coming from a pseudo-random generator. Okay. There may be cases where the truly generated random number can hit line number 24. I'm not saying that is never possible, right? All you need is one mapping, like if I go back to my whiteboard. Remember, all we are doing is we are mapping from the set of n bits. Here are your n bits, right? All the numbers are n bits, and we are mapping it to the G is basically mapping it to, in this case, to another set made of 2n bits, right? It is possible that we randomly pick a 2n bit number, right? We pick a number somewhere here. Let's say I picked this number. It could be possible that number can also be mapped by G, okay? Meaning there exists a seed that maps it. So there are random cases where this can happen when our distinguisher was called with a random R, okay, as input. Let's say I picked an R here, the distinguisher returned 1, but the brute force algorithm was able to find an S, okay, which may happen very, very rarely. That's why I said earlier, the probability of this happening is 1 over 2 power n, which is very, very negligible for large n, right? So we don't want to allow the distinguisher to run exponential time. That is the main message I want to get across. That is the reason computer scientists or cryptographers, more precisely, defined the pseudo-random generator, assuming that the distinguisher only runs for polynomial time. Okay. Otherwise, you can never design a pseudo-random generator, right? Because the pseudo-random generator, by definition, is far from uniform. And if you let the attacker run exponential time, then he will be able to distinguish your pseudo-random number from a regular random number. Okay, that's the main message I wanted to get across. I hope you find the Python notion useful, because it will help you to understand what I mean by exponential distinguisher, right? I keep calling the generator for all possible seeds until I get a hit. If I get a hit, I return 1, otherwise I return 0. That's the core idea of this program. Okay, thank you very much for your attention.